So now that we've introduced the concept, we need to find the general case. So if we're going to be taking any 3D shape and slicing it into cylinders, then we can approximate that volume with the sum of the areas multiplied by the widths. And if we take this sum, make it an infinite sum of infinitely thin cylinders, then what we're really doing is taking the definite integral of a function that represents the cross-sectional areas at that point, and adding these up. So, for example, let's start with a sphere of radius r that is centered at the origin of our coordinate system. So we have our sphere. It intersects out here at minus r. It intersects over here at plus r. That's also minus r. That's plus r. And there should be a third axis in here to represent all three dimensions. I'm leaving it out to make the diagram a little simpler. And we can slice that into various points. So what is the area of this circular wedge? Well, the area of a circle is pi r squared, but here the radius of this circular wedge is not the radius of the sphere. That's this distance. The radius of the circles changes as we move. Some are larger, some are smaller, and because these circles are centered on the x-axis, that means our radius is y squared. So, we can also use the Pythagorean theorem and build a right triangle in the middle of our sphere here. So we can see this right angle in this right angle triangle, and the Pythagorean theorem is going to apply. So in this case, once we're labeling things, we're going to have our x, our y, and our r. So y squared is going to be equal to r squared minus x squared, all by the Pythagorean theorem. So applying this in our general case, that means the volume of our sphere is going to be the integral from minus r to r of the area, which is pi times the radius of that circular slice. Not the sphere, the radius of that circular slice, which is y, and it's that radius squared, which is going to be r squared minus x squared dx. So now we are getting somewhere. Now, just to simplify things, because with volumes we always want absolute values, but with this expression we're going to have some negative volumes because that's the way the math is represented. So instead of taking the entire volume from minus r to r, we can multiply the whole thing by 2. We can even pull that pi out because it's a constant, and just sum up the volumes of the right half of our sphere. So that's r squared minus x squared dx. Now this is the integral of a polynomial. That is something that we haven't really had an issue with before. This is 2 pi. The integral of r squared, where r is constant with respect to x, is just r squared x. And then here we have a 1/3 x cubed, and that is taken from 0 to r. So evaluating this further, we're going to have this expression when x equals r, which gives us r cubed minus 1/3 r cubed, minus r squared x when x is 0, minus 1/3 x cubed, or plus, sorry, because we're subtracting the negative, 1/3 x cubed when x is 0. So our v is 2 pi times r cubed minus 1/3 r cubed is 2/3 r cubed, plus or minus 0. The 2/3 times 2 gives us 4/3 pi r cubed. We have now derived the volume of a sphere. Next up, the volume of a right cylindrical cone.